Good morning or good afternoon, depending on where you are. We are continuing with our thermodynamic lectures. Today we look at distillation of liquids. Distillation of liquids. And so, if we go to a temperature composition system, that's liquid-liquid equilibrium, if we go to our temperature composition systems, we will see that we can have, as we had already mentioned in our earlier lecture on lever principle and phase rule applications, where we came up and saw systems which are partially miscible, which have lower and upper consolute temperatures, and they behave in terms of their solubility as temperature is varied differently. There are those where the solubility increases as the temperature is increased. There are those where the solubility increases as the temperature is decreased. And we saw with the, for example, water nicotine system, which had both upper and lower consolute temperatures, where above the upper consolute temperature, there's complete miscibility. Below the lower consolute temperature, there's complete miscibility. Intermediate, we had the two conjugate solutions coexisting. Now, if we have a system A of components A and B, then we have temperature, we have composition. Remember, in this direction, we are going towards 100% B. In that direction there, we are going towards 100% A. And so if we have at this temperature, we have A1 plus A2, that's A1 and B. Let's call it A1, let's call this A1, let's call this A2. Now let's just leave it as this A1, A2. Let's call that A1, let's call that A2. And we have conjugate solution here, A1 and A2 coexisting in equilibrium. And like you have said, you can use lever principle to tell the relative amounts of A and A1 and A2. So long as you have drawn a tie line, you're able to look at this length of the segments and you're able to tell their relative amounts. Now, if the pressure is low, we will have the appearance of vapor. We'll have the appearance of vapor. So we'll have liquid plus vapor if the pressure is low. That is at low pressures. At low pressure, vapor will appear. V is vapor, remember, V is vapor, and L is liquid. So at low pressures, vapor will appear. So if you continue lowering this pressure, then you know theoretically that this curve will be moved downwards and they will fuse with this other curve. Well, as you continue lowering the pressure, this curve will be lowered down. More vapor will appear, the curve will move down, and we are going to have an interface between those two systems. They will interface so that the new system which you'll have finally, you will have A and B, you'll have A and B, like we have said, more fraction of A, that direction, more fraction of A. That means 100% B, 100% A at this end here. And of course, we have our temperature. So what we are going to have is a new system. Try to draw it as best as we can. Let's try to get it as best as we can so that we have a state point there, state point there, state point there. You see what you mean? So we have A1 plus A2, A1, A2, you have vapor, you have of course A1, this one, plus vapor. And here we have A2 plus vapor. Let's say that's temperature. Let's call this temperature TA, and let's call this temperature TB. Now, we talked of distillation. Remember distillation, where you are able to separate system into its various components. If you look at what is called the condensate, when you cool it down, then you are able to separate them into different components. That's basically the process which will be going on here. So you can have large fractional distillation columns. You can have the simple distillation system, where you have the Libby condenser and so forth. But what we are saying is, let us now take a state point. Let us say that you have a state point F here. State point. It's a state point. There's a state point defined by some variables. Now, if we raise the temperature of this mixture corresponding to this state point, remember we have composition here, so you can tell the composition of that state point by simply dropping down a line here, and you'll know how much of A is there, how much of B is there, remembering that at this end you have 100% B, this end you have 100% A. So if you increase the temperature of this mixture, whose state is defined by that state point F, then you will see that, try to get the line straight, when you reach the intersection with that curve there, when you reach that intersection with that curve there, let me give myself a little room by pushing that curve a little bit higher up to give me a little bit of some room. Yes, that's better. A little bit of some room. Yes. If we reach that particular state point, we will have vapor forming at that point. That vapor forming that point, and the composition of that vapor will be given by E. E is the composition of the vapor. E is the composition of the vapor. So as you raise the temperature of the mixture whose state is given by this state point here, you will continue increasing the temperature. When you reach that point there, you will start forming vapor, and the composition of that vapor will be E. The composition of that vapor will be E. Pay attention to that. Now, when you cool this vapor, you cool it down, it will end up this point here. Let's call that G. That state point G, in the region where we have the two conjugate solutions, A, A1 and A2. So you started with a homogeneous mixture, and now when you are cooling it down, when you've raised the temperature at that point, when you cool down that vapor, it will now have two liquids, A1 and A2, whose relative amounts are given by the Lever's rule. What you do is draw a tie line. A tie line, and this is discussed in the lesson dealing with Lever rule. We talked about tie line, and so from the relative amount, the relative length of these segments A1 and A2, we can tell the relative amounts of these two liquids, because the amounts of the liquid A2 in this system at this state point is given by that segment, and that for A1 is given by that particular segment. What are we saying? That is the number of moles of A1 divided by the number of moles of A2 are given by the ratio of the segments. For A2, that segment X1, And for A1 is that segment X2. So the length of those segments will give you the number of moles of A1 and A2 in this region. You started with an homogeneous mixture, now you have ended up with two liquids. Now, suppose we decide that we now heat this liquid which we started off with. Now we start heating it back to that system there. We are starting to heat it back to, we are raising the temperature. What happens? Now, let us look at it on a fresh diagram so that you don't get confused with the drawings there and the markings which you have on that diagram there. Let us redraw that diagram here. A, B, X of B, X of A, again temperature, composition, getting the shape the way I want it, trying to get it as best as I can. Let me see. Okay, that's not bad. Now, we are having that our state point. Let's call it again G here. We call it G, and our temperature still remain. Let's mark that as TB, and that one as TA. Remember, that's 100% B, 100% A. We are at state point B. Now, this is, of course, vapor. And we have A1, A2, A1 plus A2, and of course, A1 plus vapor, A2 plus vapor. Now, when we now increase the temperature of this mixture at state point G, which we have just redrawn here so that you don't have those many writings there. We have it here. We know the amounts we have said you can get from Lever's rule and so forth. As you raise the temperature, pay attention, as you raise the temperature, the relative amounts, of course, will be given. If you draw a tie line there, the relative amounts, we said X2, X1, you can see from Lever's rule, as you continue increasing the temperature, the relative amount, this fraction, this component having X1, which represents the number of moles of A2, decreases. That in other words, A2 is being preferentially vaporized as compared to A2. You see the length of the segment X1 will be decreasing. That length of that segment is decreasing. Length of segment is decreasing relative to that of A2, X2. X1 is decreasing. Let's call that X1 prime. So you see it decreases. In other words, and this segment X1 represents the moles of A2. This segment A2 represents the moles of A1. So as this segment decreases means that A2 is being preferentially vaporized as compared to A1. Now, when you reach this point here, the temperature becomes constant. The temperature will become constant and the system becomes invariant because you have three phases coexisting in equilibrium. We have three phases coexisting in equilibrium at this particular point. Let's just call them K1, K2, K3. The three phases are coexisting in equilibrium. Now I can erase this. What does that mean? We say that because the temperature is kept constant in this whole process, the first rule we say that with constant pressure is C minus P plus 1. Normally it is plus 2 when the temperature and pressure are there. If you keep one constant, pressure or temperature constant, you are left with one variable there. If you keep both of them constant, then the first rule will be C minus P, because you have kept the others constant. Now we have kept pressure constant. I've marked it with a suffix to indicate pressure is constant. I've indicated with a suffix there, pressure constant. So where we have the three phases coexisting in equilibrium, we have two components, A and B. We have three phases coexisting in equilibrium plus 1, so we have 0 as the variance. So the variance is 0, or the number of degrees of freedom is 0, or number of degrees of freedom. Or freedom is 0, that point. And at this particular point, the temperature is constant. A2 is being preferentially vaporized. Temperature remains constant where we have the three phases. And finally, after that, as you continue heating, the temperature now rises, and we are in the region where we have A1 and A2. We are in the region where we have A1 and A2. And now we'll have the vapor curve following, in this particular region, following from K2, let's call that M. The vapor curve will now move in that direction from K, the composition will vary from K through M at that particular point. We have vapor, and of course we'll have A1 again. You can still tell the relative amounts of those two phases using Lever rule. Very important for us to note. We have looked at the distillation. You started in a homogeneous region. You raised the temperature, vapor was generated. When you condense the system, you ended up in the two-phase region where you have the two liquids, the two conjugate solutions coexisting together in equilibrium. They are called conjugate solutions coexisting in equilibrium, and you can actually tell the relative amounts by just doing a tie line and using Lever's rule, like you already said, so that you know the relative amounts. Now, when you take that quantity, that particular state point corresponding to G, which has the relative composition, which you can read from the composition axis, and you now heat it up. You raise the temperature. We reach the point where we have the three phases coexisting in equilibrium. The temperature will be constant at that particular point. The variance is 0 for some time, and A2 will be preferentially vaporized. Preferentially vaporized, you are left with A1. That's why you're not seeing A2 in this region here, because A2 has been completely vaporized. And now you have the vapor and, of course, the liquid A1, and the vapor curve, that's the composition of the vapor, follows the curve K2, K1. So in the same way, you can vaporize. You can change the temperature of some component. Let's say this is L, let's call it P. Again, if you do the same process, you will see that vapor will form, and if you cool it down, you'll end up in the two liquid region. If you repeat the same process, you'll see the same thing. Three-phase region invariant, temperature will be constant, and then when finally A1 now will be preferentially vaporized, and then we'll have A2 and vapor, and the process continues. So let us stop at that point. We'll pick up with other lectures later.